Hello, my name is Alex Lovesey of Voss Scientific, Principal Investigator for the development of this ultra-short pulse laser diagnostic system. At the request of the Navy Directed Energy and Electronic Weapons Program Office, our company has developed a compact portable instrument package we call LUCS that provides full single-shot characterization of ultra-short laser pulses. With a swap of less than a cubic foot, 20 pounds, and 50 watts, the system is easily deployed by a single operator in less than an hour and is equally at home in laboratory and dynamic field environments. The built-in data analysis provides the operator with the physical properties of the laser pulse in a live display, which can be accessed on any device using a standard web browser. The standard network interface intrinsically supports remote operations via wire, fiber, RF, or even autonomous collection. Voss Scientific has been involved in directed energy research for well over 30 years, beginning in high-power microwave and pulse power development. We expanded into ultra-short pulse lasers more than 20 years ago. During this time, we've conducted numerous laboratory and field experiments on laser propagation, material interactions, nonlinear effects, and sensor interactions. We have also developed several novel laser systems, including a 1 nanosecond, 400 millijoule, and an 80 picosecond, 140 millijoule, 1 kilohertz neodymium YAG lasers, a 1 nanosecond, 100 millijoule, 1550 nanometer OPA laser, and a 350 femtosecond, 8 millijoule, 100 hertz, 1620 nanometer OPCPA. Our team of multidisciplinary experts has provided numerous theoretical and experimental solutions for research in electromagnetics, ranging from DC to high-energy particles. The team includes both experimental and theoretical expertise in mechanical, electrical, software, high voltage, RF microwave, optical, laser, and particle physics. As part of this team, the developers of the LSP PIC code continue to advance the state-of-the-art with the release of the Chicago Suite, an advanced three-dimensional fully electromagnetic particle and cell code designed for executing multi-scale plasma physics simulations. Voss Scientific is also very active in the SBIR program, which has resulted in multiple Phase 3 awards, including the first Phase 3 in the Air Force, called DAC, for data acquisition, archival, analysis, and instrument control. This fully commercialized product is used by the DoD, DOE, educational, and commercial institutions. Voss Scientific offers a wide range of available resources, including laser, pulse power, and microwave laboratories, and a portable clean room laser laboratory. This facility has multiple ports for beam propagation experiments, including a roof-mounted port and structure to accept a 12-inch beam director, and it can be easily transported for remote field testing. The objective for this work is to develop a compact, robust, easily transportable, fully integrated, and user-friendly instrument suite to characterize ultra-short laser pulses. The system provides characterization of all laser parameters, including pulse energy, spectrum, spatial profile, and pulse duration, including long-duration pedestals around the main pulse. All of the instrumentation is controlled through a single user interface, which provides a holistic view of the pulse parameters. The solution provided by Voss Scientific is built on our 20-plus years of experience conducting the same types of tests the Navy is interested in. Visible at the very top of the upper figure on the right is a small box labeled CDS. This is the predecessor to the LUCS developed in this program. The system shown in the model and fully assembled in the lower image was developed for a series of flight tests. The bulk of the system shown in these figures is made up of the large collection aperture, the pointing acquisition and tracking system, beam reduction, various optical experiments, and the control electronics on the top of the lower figure. Traditional techniques used to characterize ultra-short pulse lasers consisted of a collection of instruments purchased from different vendors or assembled by researchers. Each instrument required its own computer and software and saved the data in its own file format. Scientists were required to set up all the instruments, design an optical system to provide the manufacturer's specified input beam parameters for each instrument, and then operate each system independently. After the data was collected, each file is converted and imported into the data analysis software used in that laboratory. processed using the necessary correction factors, and combined to arrive at the final result. This process can require multiple days to set up and sometimes fill an entire 4 by 8 foot optical table. Collating and analyzing the results often requires customized software to deal with the various file formats and hours to process a full set of data from a single laser pulse. Because of the required investment to process a full set of data from a single shot, experiments often collected only a representative shot or a statistical representation of a burst of shots. This placed unacceptably large error bars on the data and eliminates the ability to compare the results from a single experimental event to the parameters of the exact laser pulse. Beginning in the late 1980s, Voss Scientific pioneered the development of computer-based automated data acquisition, archival, and analysis for single-shot and repetitive single-shot high-power microwave events. Using standardized graphical user interfaces, this software integrated multiple, eventually hundreds, of diverse instruments into a single system controlled by a single operator. Physics-based data reduction algorithms were implemented in the software to automatically convert the raw recorded signals into the physical quantities desired by the researchers. When Voss scientists were recruited to support USPL experiments in 1999, the same techniques were used to upgrade the software to support the instrumentation and analysis algorithms unique to this field. In addition, new operating modes were required to support the continuous operating nature of the lasers compared to the triggered operation of typical HPM systems. In parallel with the software improvements, designs for miniature individual diagnostics were developed, leading to integrated systems. The USPL diagnostic techniques developed have supported numerous laboratory and field tests in environments including desert, maritime, and aircraft. One early example of this type of system is shown on the right. The upper image shows a 3-foot square breadboard containing a fully integrated laboratory diagnostic suite for a 1.6 micron USPL. This system consists of a single-shot frog, long-pulse autocorrelator, multi-channel spectrometer, energy sensor, far-field camera, and near-field beam profile camera. The system has a single optical input and includes all of the beam splitters, telescopes, and alignment tools fully integrated to allow easy installation and operation. The electronics were also integrated into a single rack shown in the lower image. The electronics provided fully synchronized trigger control for all of the instruments and can also be synchronized through GPS timing technology with multiple remote test sites. While large and cumbersome compared to the less than 1 square foot size of the LUCS, this system represented a true breakthrough for its time, especially considering the wavelength it supported. The culmination of this work is the live USPL characterization system, or LUCS. This single-shot device integrates all of the USPL diagnostics into a single package occupying less than 1 square foot. The LUCS is available in different configurations based on the wavelength of the USPL. We have already demonstrated a visible to near-infrared version and a near to shortwave infrared version. Development is underway for a midwave infrared version. The most capable model can be used with lasers operating from the middle of the visible range through shortwave infrared. The specifications for this multispectral system are shown on the slide. Note that a wide range of collection optic sizes are available, and these can be switched based on the experiment configuration. The largest shown on this slide is 300 millimeters in diameter. However, larger apertures are possible if needed. The reason for this large size is the anticipated use in long-range propagation experiments, which typically incur a significant amount of beam profile distortion and beam pointing jitter. These variations require the ability to collect over a larger area to ensure the probability of success is acceptable. Due to the high-quality optical design of the collection system, the resolution is still less than 2 millimeters for this aperture. The LUCS can also be operated without an external collection system, using an input aperture as small as 11 millimeters for laboratory use. This results in a resolution of 150 microns. Most USPL pulse width measurement systems are designed to characterize the detail of tens of femtosecond pulses, but cannot measure anything longer than a few hundred femtoseconds. The standard pulse width measurement used in the LUCS can accurately record all but the shortest of pulses, and the relatively broad temporal range will detect residual pedestal or even multi-pulse behavior within a 6 picosecond window. If a more extended temporal record is desired, high bandwidth photodetectors can be integrated into the system, providing better than 20 picosecond resolution depending on the recording instrumentation. The specifications of the spectral measurement are highly flexible and can be easily customized for the exact requirements of the user. The spectrometer can also be changed for future scenarios. For example, a system configured specifically for 800 nanometers could have a spectral range of 300 nanometers and a resolution of 0.3 nanometers. Alternatively, it could be configured to cover 600 to 1100 nanometers, including both titanium sapphire and ytterbium YAG lasers, while still maintaining a resolution of 0.5 nanometers. The system can also support dual spectrometers to examine harmonic generation or fluorescence phenomena. The minimum energy system can detect is 0.5 microjoules. While at this low level, no pulse width data can be extracted, all other diagnostics are available. To achieve a full data set requires about 100 microjoules, depending on the pulse width and beam diameter. Higher energy pulses can easily be accommodated by sampling a portion of the total energy. This technique diverts the bulk of the laser energy into the experimental setup in parallel with the small fraction which enters the measurement system. This allows simultaneous synchronized collection of laser parameters and experimental results, which is critical to understanding observed behavior in the highly variable conditions encountered in long-range field tests. The system is capable of recording single event data for lasers with repetition rates up to 1 kHz. However, the data readout rates for some sensors limit the collection rate to as low as 100 Hz, meaning that some diagnostics would report only every 5th or 10th pulse. Additional limitations exist at repetition rates beyond 1 kHz. Depending on the exact configuration, a typical system occupies the space of a letter-sized sheet of paper with a height of less than 6 inches and a weight of less than 10 kilograms. The power requirements vary, but can be less than 50 watts total, meaning that the system can easily run for a full day on a small battery. As previously described, the integration of the software to control all of the equipment, automatically analyze the data, and provide a single display to allow researchers to understand the laser parameters at a glance reduces hours or days of work to a fraction of a second. The software provides a web page that can be easily accessed from any standard web browser. The configuration of the page can be adjusted depending on the device used to display the data. For example, on a standard computer monitor, the display of waveforms and images provides additional detail. While on a smaller device, such as a tablet, the display can be reduced to a set of bar graphs to provide complete information. To produce the bar graph display, the software automatically applies the reduction algorithms and extracts the key values from the data, like pulse energy, spectral width and peak, beam height and width, pulse width, etc. Additional processing options can combine data to produce the results like peak intensity or fluence. Each graph shows the result of the last measurement and the running statistics for a user-defined number of shots. In addition, the user can set upper and lower warning and error thresholds for each figure of merit, which are also displayed. In the event the measured value crosses the warning level, the graph turns yellow, and if it reaches the error level, it turns red. This feature provides instant feedback that the system is performing within the desired specifications, and an obvious indication when there is a problem. The near-infrared and shortwave infrared design of the LUCS are complete, and prototypes have been tested in laboratory and field environments. A new design for the mid-wave assembly has been completed, and the design is being reviewed to determine if a common optical design can accommodate all of the different wavelength systems. Most of the hardware for the mid-wave version is on hand. However, due to supply chain issues, we do not have a mid-wave infrared source on hand to begin laboratory testing. We anticipate the source to be available in early May 2022. The LUCS software is fully functional, and additional improvements are ongoing to produce a polished commercial version. The ability to place a single compact instrument in the beam and be able to view all of the key laser parameters in a matter of minutes is a game changer for USPL researchers. Viewing the live display of process results anywhere in the lab on a wireless tablet or laptop provides real-time feedback for laser tuning and experimental setup. The same capability is available in a test range setup. By using the existing network infrastructure or a temporary microwave data link, the received data can be viewed from the transmit site, supporting rapid laser alignment and maximizing the amount of limited field test time available for the planned experiments. The automated data analysis provides the desired physics parameters directly to the researchers, eliminating hours of work in collecting and converting files, processing images and waveforms, and collating results from separate instruments. At present, global supply chain issues have left us without a working USPL or any midwave laser. We anticipate this to be resolved in May of 2022. This is beginning to impact the development of the midwave IR system, which should be in laboratory testing now, March of 2022. In addition, recent improvements in the shorter wavelength systems have only been able to be tested using low-power diode lasers. In the meantime, we are working on software improvements and final integration of the system electronics. On a more positive note, we have provided a quotation for our first commercial system and anticipate delivery before the end of fiscal year 2022. There is ongoing research in USPL development, propagation, and effects at multiple DoD and DOE facilities. We already have relationships with some of these researchers, and they are aware of the LUCS work and have expressed substantial interest. As the development moves toward a fully commercial version, we anticipate several of these facilities will become LUCS customers. As previously mentioned, we expect our first delivery later this year, and there will be a number of parties waiting to see how the system works in the hands of non-Voss personnel. Later this year, the mid-wave infrared version of the LUCS will be ready for testing. We are searching for a partner with a USPL in the 3 to 5 micron range to demonstrate the system in a field experiment. If you have or know someone who has such a laser who would be interested in some diagnostic support, please contact me. If you are a USPL researcher who is frustrated with the time and effort required to configure, collect, and analyze USPL measurements, or know someone who is, please contact me. If you are planning a future field experiment, we can certainly make your life easier and likely provide higher quality data. Thank you for your attention.